We're now going to talk about standing waves. In chapter 16, we only talked about traveling waves. So it's important to understand how a standing wave and a traveling wave are different. In the next video, we'll try to understand how traveling waves can make standing waves, but even if you don't fully understand that, you can still analyze what a standing wave on its own. So this is going to be a very typical picture of a standing wave. So we have a string, and this end is vibrating slightly. Not very much. We can actually imagine that that point is fixed, but this is vibrating a little bit. And then this end is fixed as well. Now what you probably notice is that it looks kind of like a wave, but these points are zero. You might also look and say, oh, there are 5 different strings here. That's not actually the case. This is actually summing up pictures taken at 5 different moments in time. So this is 5 different moments in time, and it's a little bit tricky to know which part of the string goes with what. But if I trace out one moment in time, it goes up, it comes down, and it doesn't go back up again. It actually keeps going down, and then comes up, and continues up like this. So when I trace this single one out, you see that that looks like a sine wave. It's only part of a sine wave, and I can trace out a different one that would actually correspond to a different moment in time. Still a sine wave though. So a standing wave is going to be a sine wave. It's sinusoidal, but it's actually just going up and down. And there are certain very important points that stay zero. So you see that here we have a maximum back and forth. Here we have a zero back and forth. So we're going to call these nodes, we're going to call these antinodes. So this peak isn't moving to the right. Nothing is really moving to the left or right here. We're just taking our individual string and it's going up and down. So this is going to be quite different. So it can be helpful to actually look at this broken up into different pieces in time. So now we're going to try to do that, and notice that this picture is really wide, so the one down here actually then continues back up here, and those are actually identical. So initially, we are at some t0, and we can watch one spot on the wave. And what's helpful is to actually draw an equilibrium line. Draw the point that corresponds to a displacement of 0. And of course, I'm not particularly good at that, but hopefully you see roughly what I'm trying to do. So now you can see a little more clearly that our marked location in blue is going up and down. And so initially it's down, it becomes, in this case, it goes a little more down, then up, it goes to the equilibrium position, it keeps going up, this moment's the same moment as that, it goes up, comes down a little, 0, and then down. So the other thing to notice is if we call this t equals 0, we still have a period where it is back to where it started. And we can still define a wavelength. Now be careful because again our wavelength needs to be from peak to peak, and the wavelength is preserved. So in a standing wave, the locations of our peaks don't change, so the spacing of our peaks don't change. So individual points are still going up and down. And when we watch, in this case, a maximum, we don't see the maximum going to the right or the left at all. So this is the idea of a standing wave. So you can imagine that if we actually added up what all of these looked like in time, then we would get back to that same sort of picture we drew before. And that's what you're normally going to see for a standing wave. You're not always going to see it broken up like this, but we usually draw something more like this to communicate the idea that it's going up and down multiple pictures in time. So this would be like a sum of all of these. So that is what a standing wave is. Again, it's still sinusoidal, but it's very different than a traveling wave. So one of the important things to understand about the terminology are nodes and antinodes. Nodes are where it's 0, and in that case it's always staying 0. There is going to be certain moments in time where the wave is back at equilibrium. However, these special locations, the wave is always at equilibrium. You have zero displacement here at all times. These maxima are called antinodes. And the spacing between nodes is actually the wavelength divided by 2, not the wavelength. But the reason for that is to remember that your wavelength is an up and a down. So you do have spacing between these points, which is lambda, but you actually have another node in the middle, which is why it's lambda over 2. So frequently we're going to be identifying what standing wave we have based on counting the number of nodes. So that's where it's important to remember which one are nodes and which one are antinodes, because we might need to talk about how many nodes or how many antinodes are on a specific standing wave. The next thing to think about is what the intensity is going to look like. And this relates to certain phenomena we're going to talk about. So the intensity goes as our amplitude squared, right? So our intensity is proportional to amplitude squared. So because there's certain places that are zero, there's actually zero intensity there. There are other places where you have maximum intensity because your amplitude there is maximum. So again, we see that we have this changing amplitude, where in this case, this is now going to be a function of position and not just this A. So what this is going to correspond to, for instance, if you imagine a standing sound wave, here it's quiet. You actually would have no sound. Here, where your intensity is big, it's loud. So we might talk about places, locations, where sounds are louder than they are in other locations, and that has to do with these standing waves, so that you actually have intensity that is varying with time. So we'll explore this a little more in the subsequent videos.